The next section of this chapter is going to be about gravitation. We're actually going to split this up into smaller chunks, so hopefully it'll be a little bit easier for you to understand. So today we're going to cover universal gravitation with Newton's logic and Newton's math. Let's start with what Newton was thinking. You've probably heard the story about how Newton was sitting under a tree and an apple fell and hit him in the head. While I'm not sure how true that is, it did lead him to start thinking about what made things fall down. So the story goes that he saw an apple fall and he concluded that it fell because the earth attracted it. And then he started wondering if this same force extended beyond the trees and the clouds that you could see and even more into outer space. And Newton concluded that gravity was in fact the force that attracted the planets to the sun. This is really important because it's the first time that science extended to include objects in space. Now, to lead up to an equation for what this force of attraction would be, Newton was applying his own laws. So hopefully you can remember what Newton's third law was. I gave you a little bit of a reminder, a little refresher in case you don't. But the third law stated that every force is accompanied by an equal but opposite force. Newton applied this logic to the earth attracting the apple falling down. So based on the third law, he assumed that the same force of attraction could act between any two masses. If you think about the Earth here, okay, here's our forces. They have the same magnitude but the opposite direction, so they're the same size. But we don't notice the Earth moving. However, we do notice the apple falling. And the reason for that, if we think about from Newton's second law, how force is equal to mass times acceleration, if we look at the acceleration for the apple, it has a large acceleration compared to its little teeny mass. Okay. On the other hand, the Earth has a great big giant mass and a little teeny weeny acceleration that we don't quite notice. Because the mass of the Earth is so big, we're not actually noticing its acceleration, but there is that exact same force of attraction between the apple and the Earth. But based on our perspective, we're only noticing the apple falling and moving. Newton further concluded that this same force of attraction could act between any two masses at all. And here's the equation that he came up with. The universal law of gravitation is this equation. We've got the gravitational force, and we're using a capital G instead of a lowercase g, because this is the universal law of gravitation. It's not simply the gravitational force on Earth that we've been referring to as the weight previously. So you want to be really careful with your subscripts. This is a capital G. This capital G is a constant. This number will be provided for you. It's 6.67 times 10 to the negative 11th, and these are the units. We're going to multiply that gravitational constant times mass number 1 times mass number 2. And then we will be dividing by the distance squared. This G constant that's plugged in, you can think of it more as a mathematical correction. It helps us in looking at the size of a gravitational attraction between any two masses, and also the units are put in there so that we do end up with units of simply newtons for this new gravitational force. And this particular equation is what we call or refer to as an inverse square law. Hopefully you know that what an inverse relationship means. So in this case, the force on one side is inversely related to the distance. However, because the distance is squared, that's where we come up with an inverse squared law. And we're going to take some time and talk about what that means. So we're going to use that proportional notation that we talked about in Chapter 1. And we're going to look at the difference between direct and inverse relationships with this law of universal gravitation. So for example, we want to look at how the force is directly related to each of the two masses. If we were to change one of those masses, the gravitational constant isn't changing and the distance between them is not changing. So we're only interested in these two. If I double one mass, because it's a direct relationship, I double the force. If I were to triple one mass and leave the other one alone, I would simply triple the force. So it means it's 3 times as greater with 3 times the amount of mass. Let's say I were to change both of the masses. If I doubled one mass and this one right here, that should be a subscript. So I doubled mass number 1, but I tripled mass number 2. The way that that would change my force is I would simply multiply 2 times 3, and that would tell me that my force is 6 times as big. And it works with fractions as well if you are decreasing the mass. So if I were to take away some of the mass of mass number 1, but leave the second mass alone, I only have a coefficient of a 1/2 in front. Since it's a direct relationship, my force is going to be 1/2 as big. So let's try 2 more. If I were to make one of the masses half of its original size and double the second mass, I'm simply going to be multiplying 1/2 times 2, and that gives me 1. What this does is it tells me that those two effects cancel each other out, and I end up with my original amount to the force. The next one, if I were to cut one of the masses in half, and I were to quadruple my second mass, to figure out the effect that would have on the force, I would simply multiply those two coefficients, 1/2 times 4, and this gives me a 2. What that does is it tells me that those two effects combined are going to end up doubling what my original force was. Next, let's look at the inverse relationship of the force and the square of the distance between them. One thing I forgot to mention is that when we look at this formula for the universal law of gravitation, we had written it like this on the previous page. You can actually make these subscripts right here anything that you want. So I could have said, for example, mass A and mass B instead of mass 1 and 2. It's just a way, as long as you can distinguish those two masses and know that they are different, you can make those subscripts whatever you want. The other change is that right here, you might see that distance written as an r or a radius instead. That's okay. It can be any distance that's separating your masses. So if you see that written as the gravitational constant times any two masses, you can also divide by the radius squared instead of just a distance. It's just a specific type of distance, so it's okay that that's an r if you see that instead of a d. So let's get back to that inverse relationship. With this one, we want to look at the inverse relationship of how the force is inversely or indirectly related with the distance or radius squared. So here, when you see a change in 2r, what you would be doing is plugging in a 2 where the r would be. You want to plug in that coefficient and then square it. This turns out to be 1 over 4, and that's how we get an answer of 1/4 of the force. For the next one, we've got 3r, so remember you want to put the force being proportional to 1 over, so we're going to leave that 1 as a placeholder, and then this time it's 3r, so we've tripled the distance between our masses. The 1 stays in the numerator, and then 3 squared would be a 9, and that's how we get 1/9. So all we're doing is plugging in the coefficient that you see in front of that distance and seeing how that affects the force. So I'm going to do the bottom two with you. If we were to change that distance by 4, we would simply look at the inverse, so a 1 on the top. We've quadrupled that distance, but remember it's an inverse square relationship, so I want to square the 4, and that gives me 1 over 16. So my new force is 1/16 of the original value. For this last one, we would do 1 divided by a 4th, and we're going to square that coefficient on how we've changed the distance between the two masses. This is going to give me a 1 on the top, and then in the denominator I've got 1 divided by 16. So hopefully you know that you should multiply by the reciprocal on the top and bottom to get rid of that double fraction, and this would give me an answer of my force being 16 times the original value. So let's combine these two effects. I want to look at the proportionality of the force being directly proportional to the two masses and inversely proportional to the distance between them squared. So the distance squared is in the denominator. For my first example, I'm going to double one of the masses, leave the other one the same, and double the distance between them. So these are the changes I'm making. What I'm going to do is substitute into my proportionality the coefficients. So I've doubled one of the masses, so I'm going to put a 2 in for that one. I did not change my second mass, so I'm going to put a 1 as a placeholder. On my distance, I doubled it, so I'm going to say 2, but remember the distance gets squared. This is going to give me 2 divided by 4, and that tells me that my new force is 1/4 the value of my old force. Let's try another one. For this new example, I'm going to triple one of the masses, double the second mass, and quadruple the distance between them. So in order to do this, I would simply look at my new force as being proportional to 3, because I've tripled the first mass, times 2, I doubled the second mass, and then I quadrupled the distance, so the inverse part of that proportionality is going to be 4 squared, because I quadrupled the distance, and remember it is squared in our proportionality, so I'm going to write that squared sign as well. Now I simply multiply these two numbers together on the top, and I get 6, and then 4 squared is 16. Now you can reduce this down, and you would get an answer of 3/8 of your old force is the value for the new force. We'll do one more. For this next example, I'm going to quadruple my first mass, cut the second mass in half, and triple the distance between the two objects. So my force, the new force, would be proportional to 4 for the first mass. The second mass I changed by cutting it in half. And then the distance was tripled, but don't forget, so I'm going to square that 3 on the bottom. This would give me, look at the top, half of 4 is going to be 2 on the top, and then my denominator, 3 squared, would be 9. So my new force is 2/9 of my old force. For this last one, you try it. You're going to have the first mass be 1/4 of its original value, the second mass is tripled, and the distance between them is doubled. So pause and try this out on your own and see if you get it correct. Once you reduce your fraction, you should have gotten an answer that your new force is now 12 times as big as the old force. You will have some proportionality questions on your test, so if this is still unclear to you or you would like some additional practice, make sure that you ask for help and you come in so we can go over some practice problems together.